Okay, I'm going to do a quick recording of me trying to solve test 2 for Physics 1001. Let's see how I go. So here's test paper, and I go to the back and tear off the answer sheet and tear off the piece of blank paper and the formula sheet. Good. Now I've got my formulas and everything. So let's get started. First question. Alright. Question 1 and 2 refer to figure 1 below. So it's a graph of a travelling wave, this for a fixed instant in time, and this for a fixed position. Okay, there it is, it's got its formula, and it's for one particular time, one position, the wavelength and period. So if we look at how it varies with space, with the x-axis there, we can see that it repeats. If we look at there, that's about -4 meters, and that's one wavelength. Two wavelengths takes us up to just before 2 meters. So 6 meters is 2 wavelengths, so one wavelength is 3 meters. So we look at our choices and we go, this is the only one that has got 3 meters. So I'm going to go with that. Now we should check. It says that the period is 0.01 second. So we'll look at the time graph here, and we'll see that from here to there is one wavelength, and that's 0.01 seconds. So that is indeed the correct answer. So that was C. So question C. Right. Now, second part of that. The wave speed of the travelling wave in the previous question in figure 1 is given by a fair few choices. Okay, well, it's omega over k, and if you can't remember, well, I always just remember that omega's 2 pi f and k is equal to 2 pi over lambda, so therefore omega over k is equal to 2 pi f over 2 pi over lambda, which is equal to f lambda, which I'm sure you remember is the velocity. Okay, so we'll put that in. Now 95% of you got that right, so that was a nice easy question. Now, here we have a graph, again a travelling wave, and there's two. There's y of x and t, which is the solid line, and g of x and t, which is the dashed line. And just looking at them, they look to have about the same wavelength, because that's a graph of position versus amplitude. Yeah, okay. So, they're travelling in the positive x direction, so they're going that way. And at a particular time, we've got a snapshot there. What is the wave speed and the phase difference? Okay, so the wave speed is, again, we can say V equals f lambda, and that is f is 1 over t, and the wavelength, we just do a quick measurement from here. We'll say that is one wavelength, looks to be again exactly 6 meters, so times 6, and so t is 2 milliseconds, so 1 divided by 2, calculator, I don't know how you do the exponents on this calculator. How do I raise things? E, and then how do I change the sign? -3. Okay, times 6 equals and I get 3000. So I get 3000 for the speed, so that means only that one can't be it. So now I've got to get the phase difference, right? So the phase difference. Now, if they're one complete wavelength out of phase, one complete wavelength is 2 pi. It actually means they're in phase again. So what I need to do is find what fraction of a wavelength it is, and then multiply that fraction by 2 pi. So I have a look along this picture here. I'm trying to get an idea of how to do that, and I think, oh, I know, the easiest bit is to look here and here. You can see these two bits would be in phase, in that they're both passing through the axis on the way to their peak. So the two bits that are in phase differ in space by 1 meter. So therefore a whole wavelength, as I already decided, was 6 meters. So they're 1/6 times 2 pi out of phase. So calculator, clear? Clear. No. 1 divide 6 times 2 times pi equals 1.047. Okay, so 3000 and 1.047, that one. Okay, so 3 is C. Alright. Next one, we've got a tube of length L, it's got 2 open ends. What are the frequencies that are resonant in the tube? Well, we know that if you have an open-ended tube, as you remember from high school, you can have that. So in this case we've got half a wavelength. Is that half a wavelength? Yeah, it's half a wavelength. So in this case we have half a wavelength is equal to L. Okay. Okay. And the next one would be, go there. And this one looks like it's going to be lambda equals L. Okay. And so now V equals F lambda, and V is fixed, of course, it's the speed of sound. So therefore F equals V over lambda. And so for the first one here, we've got F equals V over half. Half lambda is L. So L, so we want 2L. So that is, V over 2L. The next one here, where lambda is L, we get F equals V over lambda is V over L, which is which we can write as 2V over 2L, and it's fairly obvious that the next one's just going to be 3. Well, you have to have 2L on the bottom, it appears, and you have to have V on the top, and so we have to have L on the bottom, there and there, not squared, no. And so we've got a choice, n equals 1, 2, 3 or n equals 0. Well, n equals 0 would give us that the frequency would be 0 at the fundamental, but you don't get a 0 frequency standing wave, so it's going to have to be B. So 4B. Right. Now this was the first of the ones that was, I think, come in. Hey Ralph, I'm recording.
Oh, okay. So I come back in 5?
Yeah, come back in.
Yeah,
in 15.
Yeah.
Thanks. Okay. So this is the first of the ones that was done badly. Okay. So we have here we have spherical waves emitted, and the wave intensity at a distance r is given as b of r, and we want this intensity at one distance divided by the intensity at another distance to be 10 to the fifth. Now, the intensity at a distance r is simply given by I naught over r squared, where I naught is just some number. Okay, so the intensity just falls off as r squared. So what we want is we want I naught over RA squared is equal to I naught over RB squared times 10 to the fifth. Okay, so we're saying, just rearranging that there. Alright, so the I naughts are going to cancel out, and we're going to get RB squared over RA squared equals 10 to the fifth. But we look at the answers and they're given all in terms of A over B, so it's going to be RA squared over RB squared equals 10 to the minus 5, and then obviously we need to take the square root, so we get RA over RB is equal to the square root of 10 to the minus 5. So that's I really don't know this calculator at all. Square root brackets 1 exponent minus 5 brackets equals 0.003126. So that's 3.16 by 10 to the minus 3. And so that's that one. Okay. So for question 5 we get A. And now one that people did slightly better on, but were maybe confused because they'd seen this question before, and in the version before it asked not for antinodes but for nodes. This version asks for antinodes, alright? So here's my basic construction. There's my two sound sources, and we know they make standing waves in between them because they're waves coming in opposite directions. Because they're both in phase there, then in the middle they'll be in phase because they've travelled the same distance to get there. So this middle point here will be an antinode. Now, if you know about standing waves, you know that a standing wave has a node every half wavelength and an antinode every half wavelength. So this has got wavelength 6.8 meters, so the nearest antinode is going to be half of that, 3.4 meters along to there, and 3.4 meters along to there. Okay, so there's one at 4.7. 4.7 minus 3.4 is 4.7 minus 3.4 equals 1.3. There's one at 1.3, and 4.7 plus 3.4 equals, there's one at 8.1. And so we can say there will be nodes there, there and there, those places. If we had asked antinodes, yes, it would be there, because you get 4.7 there, and halfway between these two antinodes there would be a node exactly at 3, and halfway in between these two antinodes at 6.4 would be another node. That's not what we asked, so I better put that in 6A. Right, now mechanics. Ralph always has fun with mechanics. Ask nasty hard questions. So we've got a Harrier jump jet, can provide thrust vertically as well as horizontally. We've got one flying at constant speed of 313 meters a second at a height of 20 meters above the ground. And in this condition, its forward thrust balances the drag and its weight is cancelled by the vertical lift force, okay, from the wings. The pilot sees a solid wall 10 meters high at a distance of 1,000 meters and adds extra constant vertical thrust to pass over it with the same 20 meter clearance. The vertical force required is approximately, okay, so basically it is flying along horizontally and it has to go up and over the top of this wall. It had, and it's got to keep the same clearance. So here's ground level, here's the wall, whatever clearance that it has here, it keeps it there. So if the wall is 10 meters high, it has to go up by 10 meters. Initially its vertical speed was 0 and applies a constant force, so therefore the distance it's travelled upwards is given by S equals a half AT squared. Okay, we need to calculate T. Alright, well, velocity times time equals distance in the horizontal direction. So time equals distance over velocity. So that 1,000 meters over 313 meters per second equals 1,000 divide 313 equals point. Did I do that right? I don't think so. 1,000 divide 313 equals 3.19, we'll say 3.19 seconds. Okay, and in the vertical direction we've got 10 meters equals a half A times 3.19 squared, so therefore A is equal to, rearranging, put the 2 over there, 20 divided by 3.19 squared equals 1.96 something or other, 1.96 meters per second squared. And so now F equals MA equals 5,000 times 1.96, 5,000 times 1.96 equals 9,800. There it is, 9,800. Good. Alright, so next. This one was done quite well. So we have a spherical shell rolling across the floor, and what's its total kinetic energy? Okay, well, it's got two components of kinetic energy. It's got a half mv squared from just translational motion, and it's got half I omega squared because it's rolling. That's its rotational kinetic energy. So therefore we want the answer in terms of v squared, and we can use the linear velocity is equal to r times omega. So therefore omega is equal to v over r. So therefore I can say its kinetic energy is equal to half mv squared plus a half, now I is 2/3 mr squared, 2/3 mr squared times omega squared, which is v squared over r squared. R's cancel out, and we've got half mv squared plus a third mv squared, so it's a half plus a third mv squared, which is 5/6 mv squared. Okay, so that's that one. D. And now the easiest one. We've got a uniform disk, mass m, radius r, is suspended vertically and is free to rotate about a central axis. There it is. A force F is applied to each of the points A, B, C and D. In turn, and the initial angular acceleration in each case is measured. The magnitude of the initial angular acceleration ranked from lowest to highest is the force applied to. Well, lowest is D, because D's right down there. It's directly below where it can rotate. If you apply a force there, it won't rotate. So all of those are still possible answers. Now A and C are in fact equal. Why? Because A and C are the force there, the distance from the line of action of the force to the axle is the same in both cases. So A and C equal. So therefore D, A and C equal, then B. B is certainly the biggest because B is the furthest away. So therefore the same force applied at a bigger distance will give you a bigger torque, and therefore it will give you a bigger acceleration. So it's B. Okay, and here's a nice calculational one. On a piece of level railway track, a rail car of mass m moves at a speed u towards 4 stationary connected rail cars, each of mass m, total mass 4m. After collision, the rail cars stick together, ignoring friction and other things. The fraction of the energy lost during the collision is. Okay, so initial energy equals 1/2 mu squared. Alright, that's what we start with. Now, we have a collision and momentum is conserved. Momentum's always conserved. So we have mu is the initial momentum, and this is equal to 5mv. Okay, because before one of them is moving, mass m, at speed u. Afterwards, 5 of them are all moving, all together with some final speed v. So we can say therefore that v equals u over 5. Okay, so the final kinetic energy now is equal to 1/2 times the final mass, which is 5m, times the final speed u over 5 squared, and that comes out to be 1/5 of 1/2 mu squared. Okay, so in other words, it's now only 20% of what we started with. So how much was lost? 80%. So that's E. Now we get to this question, right? Blocks, pulleys, friction, angles. Yeah. Okay. I'll put a star next to it. Too hard. I'm coming back to it. Okay. Of course, it's a problem if you find yourself putting stars next to every question because it's too hard. Now here's a nice easy one. Gauss's law. We've got 3 surfaces and we want to find the flux through each surface in units of Q over epsilon naught. So S1 has got +2 and -2. So total charge 0. So S1 must have 0. So that, and that work. That and that don't. S2 has got charge of +2Q enclosed in it, so it'll have 2 coming out. So that one and that one work, but that one doesn't. Okay. S3, total charge in S3, well, it's -2 plus 2 is 0, plus 2 minus 2 is 0, so the total charge is 0, so it's got to be 0. So it's that one, not that one. So it's D, 12D. That was easy. Okay. This next one's a bit tricky. So we've got 2 charges of +Q here, and we've got a point up here, marked and thing. That's the Y direction there, that's the X direction there. let's have a look and see what we're supposed to be doing. We want to find which is not correct. So the y component is positive for y equals 1. Well, if we picture the electric field at any point here, it will have a component due to that charge and a component due to that charge. And so, yes, anywhere where y is equal to 1, which would be along this line here, yes, the y component will be positive, no problem. The y component is negative for y equals minus 1. Well, by exactly the same argument, yes, the y component will be negative for minus 1, so they're both correct. The x component is positive for x greater than or equal to 1. So x greater than or equal to 1 is anything on this side of the line here, and you've got both positive charges to the left of it, so yes, whatever direction the electric field is, it will have a positive x component. That's correct. The x component is positive for y greater than 0 and x equal to 0. So that's x equals 0 here, y greater than 0. So we're talking about points on this line. So if we consider the point, the field here, it'll have a component there and a component there. Because these two are the same distance from there, these will be the same sizes. And so this will give you a plus x component, this will give you a minus x component, and the total in the x direction will be 0. That is, the net field will actually just be in the y direction. So this one's wrong. Okay? It's not for x equals 0 and y greater than 0, the electric field does not have a positive x component. So that one's wrong, and so I won't even worry about the others. 13, I'll just put in D. And disturbing question, this one here. We have a square pyramid of base L and height h sitting in a uniform vertical electric field. There's the electric field going up. And magnitude 1 volt per meter. The sides of the pyramid make an angle theta with the horizontal. Right. The total flux passing through the triangular faces, that is these ones, the vertical, the ones sloping up those faces, is, well, it's a uniform electric field. So the flux in will be the flux out. The flux in through the bottom is going to be the electric field times the area, which is going to be 1 times L squared, which is going to be L squared. And so the flux going out through all of these top 4 surfaces must be equal to the flux going in, so it's L squared. E, L squared. Okay. And now on to the last question, and this can be tricky if you haven't seen it before, and very easy if you have. Okay, so we have a spherical conducting shell with a total charge of plus 2q on it. At its centre we have a charge of minus q, and what we want to do is find out at electrostatic equilibrium what's the charge on the outer surface of the conducting shell. Okay, so about conductors. First of all, there's no electric field in the conductor because the charges in the conductor are free to move. So if there's an electric field inside the conductor, the charges will move and they'll keep moving until there's no electric field. So if we've got electrostatic equilibrium, that means there's no electric field inside the conductor. So now let's just draw a Gaussian surface. I'm just going to draw a Gaussian surface here. There we are. Now, in this whole region where I've drawn the Gaussian surface, we know there's no electric field. Therefore, the flux through that Gaussian surface are 0. Therefore, the enclosed charge inside this Gaussian surface is 0. So if there's minus q here, then on the inside surface of this shell, there must be plus Q, so that the total charge inside this Gaussian surface, or indeed any Gaussian surface drawn inside the conductor, will be 0. Okay? So if we've got plus Q accumulated on the inside edge there, and that means there must be, the remaining plus Q must be on the outside edge here. Why can't it be in the middle? Well, because if it was anywhere in the middle, then I could draw a Gaussian surface outside it, and the flux through the enclosed charge would not be 0. Therefore there would be flux through it, so there would be an electric field, and then the charges would move. So plus Q in the middle and plus Q on the outside. So it's C. Okay. Right, so one hates to do it, but one goes back to the hard problem. Yeah. Right. So we have some angle here. We have some slope, some block here, and another block here of the same mass. And there's a massless cord and a frictionless pulley, and they're initially stationary. The angle theta is decreased. By decreased, we're actually going to have to make this triangle go like that, so that theta gets smaller, and our block sits like there, like so. And then it says at some point, at some angle theta naught, the blocks start to move. In other words, somewhere as we swing this out, obviously the component of gravity acting against this gets smaller, but the frictional force gets bigger, because obviously if you have it hanging vertically there's no friction, so the frictional force gets bigger. But at some point apparently the reduction in the gravitational force is bigger than the increase in the frictional force, and the whole thing moves. Okay. Now I'm going to do some guessing, because I can solve this, you can solve this. Give yourself half a day, I'm sure you'll get there. But I don't know, maybe I can't guess. Nah, bugger it. Do some maths. Right, gravity there. Okay, two components of gravity, one that way, one that way. Okay, so force acting downwards there, mg, so that translates into a force mg there. Okay, and this one here is going to be mg. Now it's times cos theta or sine theta. If theta is nearly 90 degrees, then it's nearly mg, so therefore it's going to be mg sine theta. And then it's got also the frictional force as well, frictional force, and the frictional force, frictional is anything up to the coefficient of static friction times the normal force, which is equal to the coefficient of static friction times mg cos theta, because mg sine theta acts that way, mg cos theta acts that way. So that's the frictional force. So what we have is, we have at the point where it's about to move, we have mg, the force acting up there, is exactly cancelled out by mg sine theta, the component of gravity acting down, plus the frictional force, the coefficient of static friction, times mg cos theta. Okay, it's a bit of a mess. At least all the m's go and all the g's go, and we're just left with 1 equals that. And So now we can put that over there. So we get 1 minus sine theta is equal to the coefficient of static friction times cos theta, and rearranging I get the coefficient of static friction equals 1 minus sine theta over cos theta, which is E. Okay, so I had to do it largely because I actually looked at this question before and I thought I can't rule any of these out for being unreasonable. Okay, so it's E, so question 11, go and put E in. And we're done. It wasn't too hard.